Intel or IBM said, nah, it is not going to work for us. I'm throwing it to the floor. Anybody, chip in. What is the problem? Written over here. The circuit designer's goal is to reduce the delay in the carry path, right? So I have to pay real attention to the carry path. Is this the most fastest way to design the carry path or not, right? The carry rippling will be the fastest over here or not. So here, I'm just transcribing the Boolean equation into these gates, which is functionally correct. But then there are 1 OR gate and 3 AND gates. Now I have to think in terms of the capacitances. The capacitances associated with 3 gates is higher. So I need to figure out how I can reduce the capacitances associated with the carry path. Can I do it with just by 2 gates plus 1, or rather 3 gates instead of 4 gates? So that being one of the possible answers, who can answer how I'm going to do it? Of course, I've given you the slides so that you can look at them. Just look at that and tell me the answer. Okay. Let me give you the answer because we'll remove part 1. So now, if I use full adder, which I told you at the beginning, this will be the structure of the full adder. If you go back 30 years, when all these semiconductor companies like Texas Instruments, National Semiconductors, and all those people, they're making full adder, they're using something like that, right? Now, if I use this, that is what I did in the previous slide. Here, we have separated the sum from carry out. We know that sum is A exclusive or B exclusive or C in. So I have generated the sum function separately from the carry out function. And that's where something is wrong. Okay. By trying to independently implementing them, you are missing some timing overlap between the signals when they pass through the sum logic and the carry logic. So these signals come all at the same time. X3, Y3, X2, Y2, X1, this one all come together. Probably this also comes at the same time. But then subsequent stages, the carry in gets delayed, right? So I have to pay some attention how I can restructure the adder such that we will be able to minimize the circuit path on the carry path. So that's why I mentioned about the half adder. So I can do that by implementing the full adder as a combination of two half adders, and the carry out we need one OR gate. So instead of implementing using like this, I will use one half adder where I give the data input A, B, and carry A and B, and it will be generating the propagate functions and the generate function. And then the second half adder, I'll be splitting between this and this. The sum goes this way, and the AND gate of the half adder, I put it in the carry path, and then I add this output of AND gate and this output of AND gate with a 2-input OR gate. So what I did now is that I'm kind of trying to see the overlapping of signals. By generating the propagate function and feeding the propagate functions into the carry out logic, I'm able to now reduce the carry circuitry. Instead of 3 AND gates and 1 3-input OR gates, now I am having only 1 2-input AND gates and 1 2-input OR gate. So that is on my critical path now. Not 3 3-input AND gates and 3 2-input AND gates and 1 3-input OR gates. Like in the previous case, here my carry logic is much simpler, faster, right? So I will be redesigning that in this way. I will be using the first half adder to generate all the generate functions and the propagate functions, and then I will use the generate function to the carry in to create the carry chain, and from the output of this we generate some functions, which is much faster. So when we ask you to make ripple carry adder, you should think of this. Is it clear? Not the simple Boolean equations which every book will be giving you. And that's where the difference between the logic design and the VLSI design, circuit design, right? So this is where you get payoff. So it requires 2 gates and 8 transistors to implement the carry out in this chain, right? So it will be altogether for 4-bit adder, we need 8 2-input gate delays for RCA, as opposed to the previous implementation. It had 18 transistors to implement carry out. So the delay to generate carry out is 1 2-input AND gate and 1 3-input OR gate for each stages, and 4 of them are there. So 4 multiplied by this, which is much larger. So this is first and foremost lesson, because no matter whether you use carry bypass adder or other forms of adders, you need to still use 4-bit ripple carry adder at the heart of your design. And that part of the design will look like this. Any question? All of you are okay? Keep this in mind. I mean, this is very, very important. I mean, basically, most of the people I have talked to, and I have lots of experience. I worked 7 years in industry. I have taught here so many years, and I meet all the managers and all the big shots. This is never, ever flush to the students, and they just always think in the most simplistic way. And that's where the value of your engineering knowledge, this kind of things. But this is not the end of it. Now I'm just showing the, at the logic level, what manipulation I can do to improve the performance. But once you go into the circuit level, there are still more things to do. So we'll look into some of the transistor level design. One of the ways to think of is that since carry out propagates all throughout, now this is a little bit different philosophy. Here, what we are saying is that I'm going to generate carry out first by using simple logic like this, and then I will generate the sum from the carry out. So if you do some algebraic manipulation, you'll find out the sum function can be written as, instead of this, we can write the sum functions as a, b, c in plus c out bar into a plus b plus c in. Now this is very popular, at least at the student level project, to implement that. So we use